Hello, folks. In this video, we continue with the asymptotic notation. In the previous one, we made an introduction to the algorithm efficiency, and now we will study the mathematical notation we use to answer our main curiosity. What was it? What will be the performance of the algorithm on very large input sizes? And to answer this, we'll be using some mathematical notation. Just to remember, okay, so we aim an accurate measure of the time and memory complexity of an algorithm. With the time complexity, we would like to come up with a function as a function of, this is a function in the input size, and it will provide me the number of instructions to be executed, and I will have another function that will be the space complexity, and it will tell me the peak memory usage during the execution when this algorithm is run with an input size of n. But which input, as we discussed previously, so this input can be the best case scenario. This input may be the element of the worst case scenario or an average case scenario. So in theoretical analysis, we are mostly focused on worst case scenarios, but average case scenario is also very interesting. And the best case scenario, it is not useless, but let me say less interesting. Okay. So for the asymptotic notation, first of all, at the end, we will say that this algorithm has a best, worst, or average case time complexity in some notation, okay? If this is an upper bound, we will be using the big O notation. If this is a lower bound, we will be using the big omega notation. And if this is a tight bound, we will represent it with the big theta notation. But before going to the depths of those notations, I would like to give you an example to understand what it means and what we are looking for. Let's assume you would like to renovate your house. Okay, so it is too old and you would like to change something, and then you need to make a budget, right? You start thinking about it and you say that, okay, so I will have those renovations on my house, and depending on the type of the material, what we will see when we open the pipes or whatever, okay, so it will not be exceeding some upper bound. So let me say, you say, okay, so renovation will be always less than, let me say, 10,000 US dollars for my house, okay? So that is 10,000. This is the maximum amount you will need. Having an upper bound is very good, right? Because you get prepared for the worst case scenario. That is why with the upper bound, you are considering the worst case scenario. Okay. Having an upper bound is good, but having a lower bound is also very meaningful. You say that at least I will be doing those alterations, those changes in my house. So at least I will need to use something greater than, let me say, $2,000, okay? That lower bound is also very, very useful because it tells us that if you start this job, if you start this renovation, you will need to have at least that much of budget. You will need to spend at least that much of budget. So this is the upper bound and this is the lower bound. For the upper bound, when we when we talk about the algorithms, we will be using the big O notation. We will see what it is very soon. And for the lower bound, we will be using the big omega notation. So this is the big O notation, big O of a function, okay? Big O of a function defines me a set of functions. Let me say f1n, f2n, and this is an infinite set, okay? So this means, okay, f1n is an element of big O Gn set. f2n is an element of big O Gn set. And once I have the number of instructions to be computed with my algorithm, indeed it is a function, right? If this function is included in this set, then you will say that, okay, so this is big OGN, okay? And again, remember, that is very important. Big O is for the worst case. You are making a worst case analysis of your algorithm, and whatever the function you come up with, it is in this big OGN family. Then you say that, okay, so my algorithm has the big OGN time complexity in the worst case. Same sentences can be said about the space complexity as well. So that is the same, but I will not be repeating them again. Just assume that time and space complexity, they are the same in terms of math, okay? So similarly, big omega, it is also a set of functions. Again, for the lower bound, when you see that, okay, I have the number of instructions to be executed, I have this function, and this function is lower bounded with big omega Gn if it is at least as small as this one, which means it cannot be smaller than this guy. See? And so this is the lower bound. Okay, actually upper bound and lower bound, they are not that much difficult to explain and understand. When it comes to tight bound, it needs a bit more explanation. So let me try. Okay, as we said, with the algorithm analysis, what we are curious is, in our previous example, for the renovation of this house, it needs at least 2,000 and at most, let me say, 10,000 US dollars. Okay, so that's good. And I say that, okay, so I'm making this renovation for my house, which is, I don't know, 2,000 feet square, okay? And I have another house, which is 4,000 feet square, okay? And what would be the bounds for that? This is our main curiosity, right? This is our main curiosity. So once I have the result for this one, I would like to have an idea about this one as well. Okay, since these are the functions, so this is a function actually, for the algorithmic case, this is a function, then it is fine. Okay. What will happen if I say that, okay, so when you have the 4,000 feet square house, it is not between two, it is not between 4 and let me say 20, but it is something between 4 and 200, okay? So that's not something very good, right? Because the difference in between these bounds gets bigger, okay? Even worse, when the house gets larger and larger, this difference between the lower bound and the upper bound will become so different, okay? If that becomes that much different than each other, then it will become something useless, right? So to give an example, so let me give you this one. Okay, so this is Fn is equal to n. Sorry for my bad drawing, but this is, let's say, n squared. Okay. So when n gets larger and larger, the distance between these guys becomes larger and larger. You see? So that is why between n and n squared, when n becomes large, so having the lower bound and upper bound will not mean much, okay? Because the difference in between them is so huge, this will not give you an intuition. It will not make much sense if you know that the renovation of a house will be something between $10,000 and $10 million. It doesn't mean anything, right? It doesn't mean. So, however, if I have something like, so let me draw it again. This is 2n, and let's, again, sorry for my bad drawings. Okay, this is 5n. Then it is something meaningful because, so it doesn't matter whenever the whatever the values will be in the future, so their ratio will preserve something like 5/2, right? Okay, so once you have such a situation, so we call this a tight bound. When we see the mathematical representations, it will be a lot more clear. Okay, so let's go with the big O notation. Now, here I will say that a function Tn is an element of big O Gn if that Tn is always less than or equal to C times Gn for all n values that are greater than n0. Okay. The important parameters here are what is this C and what is this n0. If you look to this figure, you say that actually after an initial n0, which I do not care what happens before, I see that this is my Tn function. This is always less than what? Less than C times Gn. That is why we say that Tn is upper bounded by the C times Gn. Okay. Okay, going back to our discussion, then what is this C and what is this N0? Not important. We have the freedom to choose them however we want, okay? So you can say that I will choose C is equal to 1 million and N0 to be equal to 1 billion. That is only up to you, but once you tell the C and N0 values, you should prove that Tn less than or equal to C times Gn will always hold. Okay, let's make an example. Okay, in this example, the function fn is given as 4n squared plus 1 million times n plus 10 to the power of 34. Okay, so I have chosen those numbers very big to show you that actually that n0 can be something really huge. And I would like to prove that this function, this fn function, is an element in big O n square family. In other words, in the big O n square family, there are infinite functions, and actually that 4n squared plus 1 million n plus 10 to the 34 is indeed a function in this set. And to show this, I will choose C is equal to 5 and N0 is equal to 10 to the 18. If that is the case, I can assure you that this function will be always less than or equal to 5 times n squared for all n greater than 10 to the 18. So we have chosen n0 is equal to 10 to the 18 and c is equal to 5. Okay, since by choosing that c and n0 values, I can prove you that mathematically this inequality fn less than or equal to cgn holds. So we say that, so the upper bound for this fn is equal to n squared. In other words, gn squared is an upper bound for the given fn function. So this is called the big O notation. Once more, I would like to repeat that with the big O notation. This is a set of functions, and what I am telling with Tn is an element of big O Gn. This means Tn is indeed an element in this set. Okay. Once we are comfortable with the big O notation, big omega notation is no different than that. The only difference is the direction of the inequalities. Okay, so let's see what it is. Again, we say that for numbers less than n0, we do not care. Okay, so whatever it is. Okay, but after this one, what happens if fn is lower bounded by gn, which means fn is an element of big omega gn, then this function should be greater than or equal to c times gn. So let's assume this is fn, okay, in the graph. Okay, so what will happen? Fn is always greater than c times gn. And this always happens for n greater than n0 and for something that I choose, for some constant that I choose. Let's look at the example. So in this example, we are given this fn function, okay, and we would like to prove that this is lower bounded by gn is equal to n. This is equal to big omega n. To prove it, what I should do is I should select a constant c and I should select an initial n0 value. Once I set this, okay, I can show you mathematically that this will always hold when n is greater than 90. Once I provide you the n0 and c values, and this inequality always holds, then I can say fn is an element of big omega gn. Okay, what is fn? Fn is this function. What is gn? Gn is equal to n in my case. Okay. So far, so good. The last notation that we will be looking is the type notation, theta, big theta notation. So with the big theta notation, we say that fn is in the set of big theta gn if fn is an element of big O gn, and at the same time, fn is an element of big omega gn. That is the point that I was trying to show you in the first slide. If the upper bound, so this is my upper bound, and this is my lower bound, if both of them is the same gn function, but with different constants, so that is fine, because the difference in between these upper and lower bounds will always be reasonable, meaningful. Okay, so this is my function in between them. I have the upper bound, I have the lower bound. Again, to show this one, I need to find C1 value, and to show the second one, I need that C2 constant, and I will say that these both hold for n is greater than n0. That is why proving Fn is an element in big theta Gn, that means I will provide C1 constant, C2 constant, and the initial starting position. If Fn is this function, I can tell you that, I can prove you that this Fn is an element of big theta n square. Why? Because if I choose C1 is equal to 5 and C2 is equal to 1, and the initial value as the 10 to the 18, then this will always hold, okay? This will be greater than 1 times n squared, and it will be less than or equal to 5 times n squared. In other words, that Fn is an element of big OGN, and that Fn is also an element of big omega Gn. If both of them holds, I say that Fn is an element of big theta Gn. Okay, so that is the story behind those notations. Okay. This is something most of the time easier than using those inequalities, using limits for the asymptotic notation. So what is Tn? Tn is my function. Okay, is my function means it is either the time complexity, Tn giving me the number of instructions, or it is the space complexity, which gives me the extra space required, okay? And Gn is the function that I will be comparing my function with. What happens when the limit Tn divided by Gn when n goes to infinity is equal to 0? Actually, one of those cases will happen, right? So let's think it in that way. Okay, Tn divided by Gn, the limit will go to 0. It will go to something constant, okay? Or what can happen is it can go to infinity. If Tn over Gn goes to 0 or some constant, 1 and 2, we say that Tn is an element of big O Gn. Why? Because we see that the growth of Gn is larger than Tn. That is why it becomes 0 or it approaches to a constant, okay? And that makes Gn an upper bound for Tn. On the other hand, if the limit of Tn over Gn is a constant or it goes to infinity, then I will say this Tn is lower bounded by Gn function, okay? So 1, 2 gives me the upper bound. 2 or 3, either this one or this one, so this will give me the lower bound. And if the second case holds, then I will say that this will be the big theta Gn, okay? Summarizing again, you compute the limit of Tn divided by Gn when n goes to infinity. If that limit goes to 0 or a constant, you say Tn is an element of big O Gn. If that limit goes to a constant or infinity, then you will say that Tn is an element of big omega Gn. If you know that this limit goes to a constant number, not 0, 1, 2, 5, 1 million, whatever, okay? Then you can say that it is a tight bound, and this function is both upper and lower bounded by the Gn function. Okay. Last but not the least, I would like to discuss the basic efficiency classes. As you see here, okay, so these notations are mathematical notations and they can be anything. So Gn function, let me write. Okay, so big O, you can write any function here, right? But actually, when we study the algorithms, we see that we have very few cases to be used as complexity classes. Okay, we say that. Okay, let me erase this one. Okay, Tn. Okay, actually, this should be not Tn. So let's assume Tn. So that's a function anyway. Okay, if the function is something constant, okay, we say that this is the constant time or constant space algorithms, okay? So this is Tn, so assume that this Tn is either in a big O, in a big omega, or big theta notation, doesn't matter, okay, one of them. If Tn is equal to 1, we say that this is constant time. What is worse than constant is the logarithmic case. If Tn is equal to log n, then we call this the logarithmic. When it becomes n, we say that it is linear. And a bit worse than linear is n times log n. We call this the log linear, and in some books it's linearitmic, same things, okay? And beyond the log linear, polynomial complexity classes start, okay? Polynomial, n to the power of some constant, okay? If that constant is 2, we call this quadratic. If that constant is a cube, is 3, we call this a cubic complexity, okay? But in general, this is called the polynomial complexity with the n to the power of some constant, okay? What else beyond those polynomial complexities? Okay, so we have the exponential one. This is not something n to the c, so this is polynomial. It's beyond the polynomial. It is a constant raised to the power of the input size. For instance, 2 to the n. Okay, remember with the order of growth in the previous video, okay, 2 to the 1 is equal to 2. 2 to the 2 is equal to 4. 2 to the 3 becomes 8. You see, it's increasing very fast. When you come to the 10th step, 2 to the 10, it will be 1,000, okay? When you go to the 20, so this will be 1 billion, okay? And when you go beyond, it will be more and more expanding very quick. What is worse than exponential is the factorial complexity class. So that is n factorial. Even 20 factorial is a lot greater than 2 to the 64, okay? Even with 20 factorial, so it becomes very huge. I find the figure here very intuitive to understand the complexities. We will be mostly focusing on the time complexity, but whenever I say a time complexity, please assume that it can be a space complexity as well. The time complexity, the upper bound of this algorithm is log n. What it means, when n gets larger and larger, the difference in the execution time will be minimal, right? Because log 2 is equal to 1, log 4 billion will be something like 2 to the 30, something like that, okay? And when this number becomes larger and larger, for instance, log 2 to the power of 64, something that I cannot read, so this will be just 64, okay? With an input size of 2, let's assume, without loss of generality, the execution time is 1 second. When it becomes 2 to the 64, okay, so that is billions of billions times greater than this input size, it will be just 64 seconds. But that is why the logarithmic complexity is very much desired in algorithmic design. Okay, I'm not even talking about the constant one. The constant means the input size will have no effect on the output, okay? It doesn't matter if you provide me an array of size 10 or 10 billion or 100 billion, the answer will be always provided in the same amount of time. What is worse than log n is ON, okay? So that means something linear, which says, okay, if you know how long will it take for an input size of 200, it's not that much difficult to assume 400, okay? So it will be doubling. It will be doubling once the input size doubles. Again, going back to our previous discussions, so these measurements are accurate, but not precise, okay? So you say that when you double the input size, expect a doubling in the running time. Why? Because this algorithm is linear, okay? And worse than linear is the n log n, but that is better than n square. I'm multiplying n with something that still depends on the input size, but this is indeed the lovely logarithmic function, n log n, okay? But with the n log n, we start feeling the pressure when n becomes larger and larger. In the future, we will see that that is the case for sorting functions, okay? When n is small, so n log n, it doesn't hurt, okay? But when n starts being larger and larger, you feel the effect of log n a little bit. Then we have this polynomial time, n to the c, okay? So you see this check sign just next to these complexities. This means, theoretically, these are all efficient algorithms, okay? If there is a solution in polynomial time for an algorithm, we call them efficient algorithms due to another paper from 65, okay? But when it turns out that the complexity is beyond polynomial, in other words, it is something exponential, a constant to the power of input size, or the factorial of the input size. So this is another story, okay? So these are really hard problems that we will be visiting towards the end if time permits. So NP hard, NP complete discussions will appear in this area. It is different than the stories here. Okay, I think I don't have anything more about the complexity asymptotic notation. So for the asymptotic notation, what should we know? What is big O? What is big omega? what is big theta? What does it mean, a lower bound? What does it mean, an upper bound? How can we compute it? And it is very useful to know the basic complexity classes: constant, logarithmic, linear, log linear or linearithmic, n square quadratic, n cube cubic, n to the power of c, that's polynomial, c to the power of n, so that is exponential, and n factorial, that is the nightmare actually. Okay. What I plan to cover in the next video is to focus more on some examples. Case by case, we will have the algorithms and we'll try to compute their time and space complexities. Okay, thank you. Take care.